All right, so before the break, we were talking about objects undergoing uniform circular motion, right? And we had gotten to the point where we'd even talked about centripetal force and some examples of that, banked curves and unbanked curves, okay, things of that nature. We're actually going to take a step back here and now talk about this formula, okay? V equals 2 pi r over t. Right? What we want to find out here is what is the effect of radius on speed, okay, for an object that's moving in moving with uniform circular motion. Right now, the idea here, should be fairly straightforward. Okay, we're going to, in this experiment, whirl a rubber stopper around and around in a circle. Okay, and that circle is going to have ever increasing radii. Okay, so we're going to be, we'll start out with a small radius, then we'll go to a larger radius and a larger radius, okay, and we're going to measure a few things while we do that on each different radius. Okay, so each radius, we will be measuring the time required for 20 revolutions. Okay, from that, we'll be able to calculate the time for how many revolutions? 1, which we call the period, okay, because period's kind of important. It's in that formula, and that's the formula we're trying to verify. So because it's nearly impossible to accurately measure 1 revolution, we're going to time 20 and then just divide it by 20 and have the period that way. Everyone kind of follow? All right, so we'll be measuring the period. We'll be checking the radius, okay, changing the radius to see on that, and then calculating the speed. We want to see if the speed changes as a result of the change in radius. In case you were wondering, I'm going over the design part right now without like outright telling you the manipulated variable is blah, blah, okay? All right, so when we're doing this, okay, a couple of things kind of, need to happen. Now, the setup is going to look like this. You're going to have these incredibly high-tech devices. They're a piece of PVC pipe, a rubber stopper, piece of string, and a mass. All right? Yes. Don't tell them. Okay. All right. So all we're going to be doing is whirling the rubber stopper around and around in a circle. Now, the key here is that the centripetal force has to remain the same, because can centripetal force also affect the speed of an object moving in a circle? Okay. So when we're looking at this, okay, that means I can't hold the string. If I hold the string while this thing's going around and around in a circle, I don't know what the centripetal force is because it can change, okay? Because it's being provided by me holding the string. So I can't hold the string. I have to hold just the tube, okay? Now, there's tension in the string, but not because of me, because of, okay, so this thing here isn't going to change throughout the experiment. Okay, it's got to stay the same. The trick to this experiment is keeping that radius constant for 20 revolutions. Okay, so you're going to have to mark on your string, okay, where that radius is at the top of the tube. Okay, and then the person doing the whirling, we'll call them the whirler, okay, is going to have to monitor that and do their best to keep that constant. Everybody follow me there? Okay, it's harder than I make it look. It's because I've done this lots of times before and I'm awesome at it. Okay, the first few times you do this, this will happen. Oh, I gotta slow down, and then you'll like, oh, if I slow down, it's gonna get me in the head, and then you'll be doing this, and you'll look silly, and that's okay. All right. So what you'll have to do is kind of, all right, I'm gonna have a radius of just 10 centimeters. All right, there's 10 centimeters. If I whirl it at this speed, it stays about right there, and I'll have a mark on my string that'll help me to do that, and I'll just keep an eye on it. Now, me as the whirler, this is my only job. Somebody else times, somebody else counts, okay, and does all that other stuff. My full and undivided attention must be on this and only this. Otherwise, I will get it in the face, and I don't want that, okay? I've only ever had one person get a black eye doing this lab. That person could have got a black eye if they walked and chewed gum at the same time. Okay, so for most people, this is fairly safe. Okay? If you're really feeling uncomfortable and would like a pair of safety goggles, I will go across the hall and get you a pair. Okay? But that's the extent of the lab, just whirling that thing around and having somebody time it and somebody count the revolutions. It's pretty straightforward. Okay? The procedure is pretty easy. Everybody follow there. All right. Okay, so we've talked about the design, we've talked about the procedure. Okay, hypothesis we haven't talked about yet. So state a hypothesis relating the radius and the speed. Remember to use an if and then statement. So the if part, okay, should probably talk about the effect that radius can have on speed. All right, what kind of relationship is that? Okay, is it, and use the proper terms. Is it linear? Is it inverse? Is it exponential? Okay, you tell me. Okay, so the if part should talk about that relationship. Okay, the and part, as always, describes the experiment. Okay, in the then part, predict your results. Okay, what's going to happen as R gets bigger? Okay, so like I said, we've talked about the procedure here. Okay, it's pretty straightforward. The radii that we're going to be using are going to be 20 centimeters, 30, 40, 50, and 60 centimeters. All right, so what you will have to do, and this string doesn't look like it's nearly long enough for that, but maybe it is. Maybe just. Okay, what you're going to have to do is mark on the string. This string I can see like 1 or 2 marks on there. Just take like a board marker. I'll put a few more out here. Okay, and mark on the string those radii. Okay, and then the person doing the whirling just needs to make sure that that marker stays at the top of the tube while they're whirling. Okay, do your best. It's obviously not perfect, okay, but do your best to keep it there. If you get going too fast, you'll find that it moves out. If you slow down, it'll hopefully move back in, okay, but sometimes it doesn't, and then you'll just have to start that trial over again. Okay, questions on how that part will work? Yes, okay, and then you're going to average the two. So we're doing 20 revolutions. We're timing 20 revolutions twice for each radius. Then we're averaging those, calculating the period, okay, all of that kind of stuff. All right. Just because there's a fair amount of observational error in what we're doing, right? Being able to accurately say when one revolution ends and the next begins, being able to reaction time that properly, there's definitely some observational error that creeps in here. Okay, so we're going to be filling in a chart like this. I think I built one in your lab report already. Okay, so you'll have your radius. So this will be 0.20 meters, 0.30 meters, 0.40, 0.50, 0.60. Make sure it's in meters. It makes a difference. Okay, your time for 20 revolutions, your average time, your period, and then your speed. Right, we're just using the formulas, okay, to calculate those. To calculate period, you're dividing your average time by 20. Okay, calculate your speeds. V is 2 pi r over t. All right, so for your analysis, I would like to see an example calculation anytime you're asked to calculate something. All right, that way if you make a mistake, I know why your numbers are out, okay, because I can go back and look at how you calculated it. Just one example is fine. You don't have to show me all of them. All right, so for each trial, average the 2 times. So just show me this plus this over 2. Show me that once. That's all you have to show. Okay. For number 2, for each trial, divide the average time. So take that average time to show me it divided by 20, given the period in seconds. Okay. For number 3, show me that operation. Okay, and so on. Now for 4, 5, and 6. Okay, these are the really important ones. Okay, number 4, identify the force that acts as the centripetal force and determine its value. Now, obviously there's tension in the string. Okay, but you need to tell me why there's tension in the string. Okay, what is putting tension in the string? That's what's acting as the centripetal force, not the string itself. Okay. Then you're going to plot a graph of velocity versus radius. Okay, remember your manipulated variable goes on the x-axis, your responding variable on the y. You have to decide which is which. Okay, and then for number 6, you're telling me the relationship between radius and speed. A little explanation there is probably a good idea. Okay, talk about your graph, that kind of thing. Okay, then same as always, conclusion, copy paste your hypothesis, explain why you can accept or reject, sources of error, 2, ways to improve them, and then you're good to go. Okay. Are there any questions? All right, we easily have enough room in this room to do this lab. Just be mindful of other people and walls and things like that when you are doing the whirling, especially when you get out to 60 centimeters. All right, you're going to be covering, you know, more than a meter or about a meter and a half worth of space while that thing's spinning. So make sure you have that kind of clearance. Okay. All right, any other questions before we get started on this? This is one, guys, where realistically you should be able to get a lot of it done in class and not have too much of it to do for homework. Okay, have at her.